Among the alternatives of clean renewable energy that have been introduced to the world, hydrogen fuel shows promising future for the future sustainability. Alongside EVs, hydrogen-powered vehicles are also thriving. What could be the benefits if such energy can be entirely produced by the nature? Greetings, our respectable audiences. We, Group 2, would like to present continuous production of hydrogen gas from glucose and xylose co-fermentation. This presentation will cover introduction, modeling and validation, scale-up of the reactor, and the discussion part. This project focuses on the utilization of molecules from the decomposition of lignocellulosic biomass, which is easy to obtain from common agricultural waste. The biomass breaks down to cellulose and hemicellulose, and then glucose and xylose, respectively. Then, the bacteria enables the environmentally friendly hydrogen production from these two sugar molecules. Our objectives are based on these 4 points. To use the raw materials that are abundant in biomass, such as glucose and xylose. To reduce the process and reaction time with the simple biomolecules like glucose and xylose. To apply the biological production instead of water electrolysis. And lastly, to increase the yield using the optimal parameters and improve CSTR. Hydrogen occupies an incredibly wide range of use. In this case, the production method was changed to glucose-xylose co-fermentation. In the scale-up, we narrowed the end use down to the transport industries. As for the reactor design for the small-sized reactor, the reactor employed batch system with a volume of 100 ml, the stirring speed of 150 rounds per minute, and the temperature maintained at 60 degrees Celsius. As for the materials, we selected the concentration ratio between glucose and xylose of 8 gram per liter to 2 gram per liter. The bacteria that enables the reaction is Thermoanaerobacterium thermosaccharolyticum, W16. The reactor was filled with the boiling medium and flushed with pure nitrogen gas. Next, hydrogen production monitoring and high-performance liquid chromatography HPLC, and the pH adjusted to around 7.2 confirmed the efficacy. Lastly, key findings are that both glucose and xylose were consumed, and the yield was approximately 108 millimole per liter hydrogen. Now that we specified the ratio to be 8 gram per liter to 2 gram per liter, the hydrogen retention time to be 10 hours, and the size of the reactor to be 100 milliliter, we can calculate the reaction order. We extracted the data from the graph provided in the paper. Focusing on GX4 plot, here is a data table for glucose consumption. By plotting the graph for the 0th order, 1st order, and 2nd order, it shows that the 2nd order has the highest R-squared value. Thus, it is the order of glucose consumption, and the rate constant K is 4.18 liter per mole hour. This is the graph and the table for xylose consumption. It is also 2nd order for xylose, and the rate constant K is 0.075 liter per mole hour. Now, for the middle scale reactor, we also checked the reaction order and determined the rate constant K. However, the reactor system was changed to CSTR because it increases the contact between the substrate and enzyme, satisfying the enzymatic reaction. The reactor design remains the same, except for the volume that was changed to 800 milliliter. Now let's see the calculation. For glucose, from the GX4 plot, the data is as in the table. The highest R-squared value is found in the 2nd order. The rate constant K is 1.189 liter per mole hour. The rate of glucose consumption is 0.001007 mole per liter hour. The proportion of xylose is obviously less than glucose. The table contains the data acquired from the graph. The reaction order is also second order for xylose, and the rate constant K is 1.305 liter per mole hour. So the rate of xylose consumption is 0.0001756 mole per liter hour. So the total consumption is estimated to be 0.001162826 mole per liter hour. Therefore, the middle-sized reactor has 34.5% conversion of glucose and 13.0% conversion of xylose. The total conversion is 29.1%. In the industry scale, we aimed at using the products from this bioreactor for hydrogen power delivery drones. So we decided to use Helicopter hydrogen powered drone as the model for Seoul Metropolitan Ultralight Logistics, as they help reduce the carbon footprint and solve traffic congestion problems. This is the data regarding the operation of the drone and the large-scale reactor. From the calculation, the hydrogen-powered drone required around 80,000 liters of hydrogen per day, or 2.462 kg per hour. So the feed rate of raw material for the large-scale reactor should be 8.46 kg per hour. As a result, the volume of the reactor is estimated to be around 733 cubic meters. As for the discussion in terms of problems and suggested solutions, 1. Biohydrogen production normally gives a small proportion of hydrogen among undesired products such as methane and carbon dioxide. So pressure swing adsorption and membrane separation will be used to solve this problem. 2. The quality of the feedstock is likely to be inconsistent due to the difficulty to prepare the inoculum to be exactly the same. Raw material quality monitoring is suggested. 3. The accumulation of byproducts will be reduced by using byproduct recovery system and cleaning the reactor regularly. 4. Because hydrogen gas is flammable, there is a risk of explosion. Gas leakage detection and shutdown system are suggested. For the limitation, on this unstable bacterial growth phase, so it easily changes accordingly to the reactor condition. 2. Fluctuating gas pressure. It affects the solubility of gas species and disrupt the enzyme efficiency. And 3. Small biohydrogen yield per reactor is quite low. Due to this issue, we are aware that the yield is not suitable to large engines like buses, so we hope to use it for delivery drones. In conclusion, the conversion of glucose and xylose into hydrogen in the small-sized reactor was analyzed, and the order was obtained. 2. The scale up to the middle-sized reactor gives the reaction order and trend that align with that of the small-sized reactor, and the reaction rate and conversion rate were calculated. In scale-up design, the reactor is expected to be an industrial-scale reactor producing environmentally friendly hydrogen fuel for logistics drone. 4. The reactor was designed by scale-up with an industrial-scale reactor aiming at producing hydrogen for logistics drones. Thanks to all these references, we are able to complete this project. And here has it reached the end of our presentation. This work cannot be completed without the great contributions of our three members. First, Min-ji Kim, the leader of the group who allocated the role and directed the progress of the work. 2. Min-ju Jung, who took care of the data analysis, calculation, and assumption for the industrial scale. Pasinyomi Pak, who provided the idea, consolidated the concepts, and prepared the presentation. Thank you for all your attention.